No, well, first of all, I would like to thank the organizers, Boyan and Eduardo. It's really a great pleasure to be here. And, I'll be talking about some work done, recent work done with Filomena Pacella, who was cited in the previous talk, and Bernardino Scunzi from the University of Calabria. And, Javier talked about some stable solutions for the semi-linear elliptic equation. I'll be talking about some strong instability for the same equation, in fact, essentially. Let me consider the problem. Well, there's a big difference between both problems because my nonlinearity f of u is equal to 0 at 0, so that's a big difference. But in any case, that's a model problem. And let me start by saying some very simple things. I'm sorry, I apologize for that. But so I'm considering this problem here. Alpha is positive in what I'll be saying. I'm considering the so-called subcritical problem. So alpha is positive, but small in this sense. It's smaller than some critical number, sub-level exponent of S. Let me consider a proxy to this problem. So this is a kind of a positive function. This is negative function, positive function. So let me just consider this problem here. So this is like the action of delta u at some eigenfunction. And it's easy to see that for this ODE, we have three stationary solutions, which is 0, 1, minus 1. And now if you start at a point smaller than 1 in absolute value, the solution will go to 0. So this is an unstable solution. If you start here, the solution will go to 0. If you start here, the solution will blow up. And this is a stable stationary solution because if you start at the point between minus 1 and 1, the solution will go to 0. And that, of course, is also an unstable solution. But in any case, this problem here has stationary solutions, global solutions, which means solutions that exist for all time and go to 0. And it has also blow-up solutions, solutions that in finite time goes to plus infinity in absolute value, at least. So the same question, that's the, as we'll see for this problem also, we have also stationary solutions, global solutions, and blow-up solutions. And, there are a very vast literature about this problem. There are many, many questions that can be asked about. For example, for a blow-up solution, we can ask what is the blow-up set? So is the solution blowing everywhere or blowing at some point? At which rate? What is the blow-up profile? If it's blowing up at one point, we can ask what is the blow-up profile of the solution. So there are lots of questions and lots of answers, lots of partial answers for this problem. We can ask about the blow-up rate and so on, so forth. But but the question that I'm addressing here is, given a certain initial value, can I say that the corresponding solution will blow up or not? That's the question I'm addressing here. And too hard to answer, so I'll be giving some partial answers. And in fact, I'll try to give some properties of the so-called, I'll be calling the global set, is the set of initial value for which the solution is global. And I'll try to also to give some properties of the blow-up set, the set of initial values for which the solution is blowing up. Okay. Let me recall some known results. First of all, there is the solution is locally well posed. For example, in C0, so given an initial value in C0 of omega, there is a solution for some time. I'll be calling always T of phi is the maximal time of existence of the solution. And it's possible to, since we have a regularization property for the problem, in fact, when the solution ceases to exist, it's because the solution is going to plus infinity in L infinity norm. Okay? So blowing up means, in fact, the solution is going to plus infinity in that sense. Okay. As already been noticed before, there's an energy associated to the problem. And so this is a Lyapunov function for the flow. And we have also this result that if you start with an energy with an initial value for which the energy is negative, then the solution blows up. This is a result that comes from the 70s. There's this famous Levin concavity argument that shows that for a bounded domain, a solution with negative energy blows up. Okay. And so we have the first example of a blowing up solution. You take an initial value phi not equal to 0. You multiply phi by lambda. If lambda gets large enough, the solution blows up. Okay? So that what I would expect, in fact, from this picture, that in some sense, large initial values will give rise to blow-up solution. Small initial values, we would expect that would give rise to global solutions, and in fact, global solutions that go to 0. Okay? So that's our, let us say, feeling. So let me define G, the set of initial data for which the solution is global. G0, the set of initial data for which the solution is global and goes to 0 when T goes to 0. And B is the set of blowing up initial data. Let us say it in this way. Okay. First remark also, it's easy to see that 0, of course, is in G0, but in fact is in the interior of G0 because it's a stable solution. You start with a small initial value, then you can use the maximum principle to show that the solution must be global and go to 0 as T goes to 0, okay, to plus infinity, I'm sorry. As I said before, this is an example of blowing up solution. Lambda phi blows, the corresponding solution will blow up if lambda is large enough. In fact, its absolute value of lambda is large enough. And for positive solution, we have also this comparison principle. Then, okay. So if we take a solution in this in the positive cone, then it's easy to see that if we take a lambda smaller than phi, then the solution coming from lambda phi will be smaller than the solution coming from phi, and it's positive. And then if the solution coming from phi is global, the solution coming from lambda phi is global also. And so, and on the contrary, if this solution blows up and you multiply by some lambda greater than 1, then the corresponding solution will blow up. Okay? So in fact, for each phi positive and or non-negative and different from 0, you have this straight line, and in fact, you have a critical value here for which separate things. Okay? So in other words, if I define G plus the intersection of G with the cone of positive solutions, this is a star-shaped domain region star-shaped with respect to 0. And a very simple question is, okay, let me put this already. 2 questions. Is G and, in general, G and G0 convex, first of all, or a more simple question, is G or G0 star-shaped with respect to 0? Let me say that it's also simple to see that G plus is convex too, okay? But, okay, anyhow. So let me now start with a sign change solution, okay? And then I multiply, that's phi. I multiply phi by some lambda, let us say, smaller than 1. Okay? This part here is smaller. Lambda phi is smaller than phi here. Lambda phi is greater than phi here. So does that give rise to a global solution or not? Let us suppose that phi is in the G set. No, to plus infinity.
Just plus infinity.
Okay, this is diffusion equation. Doesn't make sense to go to minus infinity. No, just to plus infinity. Okay? So when we look at the energy is composed by 2 parts. Perhaps let me write the energy here again. So when we're multiplying the initial energy by lambda, we've got a lambda square here, a lambda to the power, let us say lambda positive, lambda to the power alpha plus 2. Then when lambda is smaller than 1, this part becomes relatively smaller than this part. Okay, so we are pushing to the positive part of the energy. On the contrary, if we multiply by some lambda greater than 1, then we're pushing to the negative part of the energy. So we are enforcing the nonlinear part when we multiply by lambda greater than 1. So even though these 2 initial values are not comparable, we're perhaps inclined to say that the solution will be global if phi is global and lambda is smaller than 1, and perhaps if phi corresponds to blow-up solution, then we'll multiply by some lambda here. We're enforcing the negative part, and perhaps we're inclined to say that the solution will also blow up. Okay? Anyhow, it's a question hard to decide because we cannot compare. Okay, so that's the picture that we have for positive solutions. And for sign change solution, let us consider then a sign change initial value for each solution is global. Then what we can say for the moment is the following. We know that if lambda is large enough, this corresponds to blow up. And if lambda is small enough, this corresponds to global solutions that go to 0, and then that's the question. What happens in between? And let me show what can be said in a very particular situation. Let me consider the case where omega is a ball in Rn, and okay. And let me consider as an example of 5, the stationary solutions of the problem in a ball of Rn. So when we consider a ball in our N, there are many stationary solutions in this subcritical case. In fact, the solutions are obtained as follows. We just solve the problem in the whole. Okay, we solve an ODE problem. I'm sorry. I'm looking for radial solutions. I forgot to say. So let me consider a radial solution. Then for the radial solution, we have that phi satisfies this ODE. I start at some point, for example, let me call this phi. I'm sorry. I start at some point phi of 0 equal to 1, for example, and phi prime of 0 equals to 0. We must have that. And then I solve this ODE. And it's possible to show that, in fact, the solution will last forever. In fact, will oscillate infinitely many times here. So you have a countable number of zeros for that solution. And now, to produce a solution in the ball, we just have to scale the solution. So this is the phi that I'm writing here. And then we scale in an appropriate manner, and we obtain for it. So rho here is a 0 of phi. And then, OK, for r equals to 1, psi of 1 is equal to 0, because this is phi of rho, and rho is a 0 of phi. So this solves the equation and is in 0 on the boundary. So there are infinitely many, countably many. There is one positive solution and countably many sign change solutions. So we have this collection of stationary solution. And OK, let me point out that this picture is not completely correct for the case n equals to 1, because for n equals to 1, in fact, the solution is completely periodic. So it doesn't decay. So we have a periodic solution. So, OK. So nothing interesting happens for n equals to 1, because if we start with an initial, if we have this 5 here, and OK, and we multiply the equation by, multiply phi by lambda, smaller than 1. This is anti-symmetric, and of course, the solution that comes from this lambda phi will not move these zeros. The zeros stay frozen. And so, in fact, we can reduce the problem to a smaller ball. And then this corresponds to the positive case. And we know that, in fact, the solution that comes from here is trapped here. And, in fact, will go to 0. And the solution that comes here, it's possible to show that the solution, in fact, will go to plus infinity here. OK. So the picture for the case n is equal to 1 for any sign change solution, for any 5 that is chosen as such a psi, is the same as in the positive case. OK? Now let me show. OK, I think this is 2009, previous result with Thierry Cazenave and Fred Weissler. For n greater or equal than 3, in fact, what we have is the following. If I choose alpha close enough to this critical value, alpha s, and if I choose lambda close enough to 1, smaller or bigger than 1, the solution that comes from this lambda phi here blows up. OK? Let me give you an idea of how you can show this. In fact, the The starting point is this proposition. Once we have proved this proposition, then we got enough energy to try to prove the theorem. And the proposition says the following thing. We linearize the problem around those. So take any such psi, which is a stationary nodal solution. In fact, here you take any domain omega, bounded domain. You take any stationary nodal solution, not necessarily radial. And you linearize the operator the nonlinear operator at the point psi. And you look at the first eigenvector vector of this linearized operator, phi 1, and you see if psi, this solution, is orthogonal or not to phi 1. If it's not orthogonal, if this quantity I is different from 0, then we have the result. Okay? And how we prove this result is simple, in fact. You just take some finite difference. You take the solution that comes from lambda psi. You take the solution that comes from psi, which is psi. And then you divide by lambda minus 1. And you write the equation satisfied by z lambda, which is this equation. And for lambda next to 1, this is next to that quantity, to derivative of this function with respect to lambda at lambda equals 1. Okay? And also at t equals to 0, this is lambda psi, this is psi, so this quantity is equal to psi. Linear, I'm sorry?
You're using that the operator is really linear.
No. The operator is no.
Left-hand side.
Okay. No. Z of lambda satisfies this equation, okay? The left-hand side depends, okay. It depends on phi and u. Okay. Once you know u and psi, this is a linear operator, okay. But what is simple to see, if I'm thinking of the problem as a linear problem, what is easy to see from linear theory is that if we take the solution with the right-hand side, which is the limit right-hand side, then in fact, as lambda goes to 1, z lambda approaches the corresponding linear solution. Now, we know that for this linear problem, the sign of z is controlled by the projection of the initial value over the first eigenvector of the problem. So we look at the projection of the initial value psi over phi 1, which is the first eigenvector of this problem. And if it's positive, that means that for some, at some time, for some large time t, z of t will finally be positive. And so, since z of lambda converges to z of t, now if we take lambda close enough to 1, z lambda of t will also be positive. Okay, z lambda of t positive means that u of 5 lambda, the solution that comes from 5 psi, lambda psi, will be greater than psi for lambda greater than 1, and smaller than psi for lambda smaller than 1. Otherwise, if I is negative, it's the contrary. But anyhow, once we know that an initial value is greater or is smaller than a stationary solution, then it's not hard to see that the solution will blow up. Okay? The idea that, okay, so in fact, we have a psi which is like this. We take a lambda, let us say, smaller than 1, then lambda psi. It's not comparable to psi, but at some time, the solution will become strictly bigger or strictly smaller than the corresponding solution that comes from psi. And once you know that, it's not difficult to see that the solution must blow up. In fact, the idea is that the argument is the following. The solution that comes from lambda psi, if it's a global solution, it has an omega limit set. The omega limit set is composed by stationary solution. Then this must, in some sense, converge to a stationary solution. But this phi is already a stationary solution. We can show that the solution that is above psi cannot converge to psi. So it must converge to a stationary solution which is greater than psi, and that doesn't exist. There are not two stationary solutions that can be compared. So that's the idea. So the solution that comes from something that is strictly above stationary solution must blow up. Okay. I have to go there. No, not necessarily. And remark, the result is false for positive stationary solutions because, as I said before, if we start with a stationary solution and we multiply the solution, the initial value by some lambda smaller than 1, then the solution is global and is going to 0. So here, the result, this proposition, uses the fact that phi is a sign-changing stationary solution. Okay? So now we are stuck with this problem. I have a stationary solution, means solution of the elliptic problem, phi. I take the linearized operator around phi. I take the first eigenvector of this linearized operator, and I want to know if this is equal to 0 or not. Question about elliptic problems. If I know that this is different from 0, I win the game. Okay. This is false, for example, in one dimension. For n equals 1, this is always 0. Because as we said, the conclusion of the proposition is false for n equals 1. So if for n is equal to 1, no hope. So what we've been able to prove, that's the theorem, is that this is true in some situations in the ball for n greater than 3. Okay. Let me give you an idea of the proof. In fact, what happens is the following. If I take this phi that is over there, and now let me call this phi alpha. In fact, when alpha approaches this critical number alpha s, what happens is that the solution, the zeros of the solution, will start to go away. So in fact, let me call this first node of the solution. The first node will go to plus infinity when alpha approaches alpha s. And in fact, for alpha equals to alpha s, at the limit, we have a limit problem, which is a positive solution. So for alpha equals to f to alpha s, there is a positive solution for the problem, a unique stationary positive solution, which has this explicit form. Okay? And of course, we can show that for this, so if we linearize the problem around this solution for alpha equals to alpha s, it's easy to see that, in fact, it has although it is defined in the whole space, it has a first eigenvector. And we have, of course, that phi, let me call this phi s whole 1s. This, of course, is positive, because both quantities are positive, and this, of course, is positive. And then now the proof goes like that. Psi times phi. I'm sorry. I'm sorry, phi. Okay, now if I move a little bit below alpha s, then we can show that this is also positive. Okay? So this is in a very large ball. If alpha is equal, let us say, I want to take a 2-node solution, or a 3-node solution, or a 4-node solution. I have to take a very large ball. For alpha a little bit smaller than alpha s, okay? But then for a very large ball, we have this. For this ball, it's a global solution, okay? And in fact, okay, and for the other critical value, which is 0, we've also been able to show the same thing. This was published in Publicaciones Matemáticas. Is that right? That's how we say it? Publicaciones Matemáticas. With great pleasure. Okay, it's a delicate case because alpha equals to 0 is in fact the linear problem. But for the linear problem, in fact, this quantity, so the limit problem, for the limit problem, we have this for the limit problem in the other side for alpha is equal to 0. This is 0. Because psi and phi are both eigenvectors of the same problem. The limit problem is a linear problem. Psi is an eigen function associated to 0. Phi is an eigenfunction associated to some lambda 1, which is negative. And then this quantity is 0. So we have to look at the second derivative to prove the result. Okay. More details, we'll go to Publicaciones Matemáticas. Okay. So that's the end of this story. And then, okay, we have asked the question, how about n equals to 2? N equals to 1, nothing to do. And greater or equal to 3, we have this result. How about n equals to 2? Well, the difficulty of n equals to 2 is the fact that alpha s for n equals to 2 is plus infinity. So the question was, what is the limit problem that we should take in this case? We didn't know, and stop there. But fortunately, I found Filomena Pacella, which is a specialist of this kind of analysis, and she was able to tell me what is the limit problem here. And then we've been able to obtain this result, also with Berardini-Scunzi, which is exactly the same result as before, the corresponding result as before, for the case n equals to 2. That means for alpha large enough, we can take a lambda close enough to 1 such that lambda psi is in the blow-up set. Okay? So the same thing for lambda large. And the only thing we had to do, well, in fact, is to identify the limit problem first, and then, okay, work hard, because work harder, I would say. Because, in fact, the limit problem of this problem, which is known in the literature as the Lane-Emden problem, is, in fact, the Liouville problem. So that's very nice, I think. And the Liouville problem, this is the problem of finding a function psi in the whole space R2, such that Laplacian of psi is equal to e to the psi, and e to the psi is in L1. Okay? And those are just normalizing conditions because you can displace, you can delete, first of all, and move. This is autonomous equation, so you can move around with the equation, displace the equation. So this is just normalizing condition. Well, forget about this. With these normalizing conditions, we have also a unique solution for this limit problem. And also here, as before, the solution is known explicitly. It's not important, but it's known explicitly. So that's the solution. Okay? And then, okay. Now, in which sense I'm saying that that's the limit problem? I'll tell you, because I didn't write it there. You have a solution which goes like that. In fact, that's psi alpha of 0, which is greater than 1. Because I think it's interesting to write the equation. I'm solving. That's the equation. So in fact, the Laplacian at 0 is, since 5 alpha of 0 is greater than 1, this is very large. So the solution, as alpha goes to plus infinity, the solution would go like this. Okay. Then, in fact, would do something like that, in fact. I'm sorry. It is vanishing, but something like that. Okay? Well, the sense that this problem has as limit the Liouville problems is because of the following. First of all, I'll just displace the solution, or better, I just consider this solution phi alpha of x minus phi alpha of 0. That's the solution. And then by some dilation, in fact, by some dilation, I'll see that, in fact, there's a dilation. I didn't write the dilation. There is some constant. So if I take psi tilde of x equals to psi of epsilon x over something, which I think is this. I'm sorry, which is, yes, this is. It's just, I'm sorry, this is, I'm writing it wrong. I'm just considering this function and doing some scaling, which is this one. Then, in fact, this quantity phi alpha here converges to, I don't know how I call it, but I'm going to call it this phi c plus infinity, which is the solution of the Liouville problem. CL. Okay. So in that sense, that this problem has as a limit the Liouville problem. Okay. And also in the following sense, if I take this quantity here, I'm sorry. So this is not phi tilde, because phi tilde is something there. Phi bar. Okay. But it's also true that if I take this quantity here and take the alpha exponent of this quantity here, so this quantity to the alpha also converges to e to the 5 psi plus infinity. Okay. And that, of course, uniformly over the complex, because in fact, this solution psi infinity is something like that. And it goes to minus infinity as x goes to plus infinity. So the convergence cannot be uniform over the whole space, but it's only uniform over the compact of R2, okay? So now we want to compute the sign of this quantity for large alpha. And okay. First of all, we write the equation for psi, we write the equation for phi, and it's easy to see that's an equality, that this quantity, in fact, is equal to that quantity. This is negative. So, in fact, to analyze the sign of I, it suffices to analyze whether or not this has a definite sign. And, of course, it's the same thing as to analyze if this has a sign. And that's the right scaling. And with this right scaling, in fact, this quantity is equal to that quantity here, which I call I tilde. So we have to analyze this quantity here. And in fact, so that quantity here, this guy converges to e to the 5 plus infinity. This guy here converges to the... So that's, in fact, when I do this, in fact, this a scaling, and in fact, the same thing. I was in the ball. I'm now doing the same computation in a large ball. So omega tilde is a large ball. And, okay, and in a large ball, for alpha large enough, this quantity is near this quantity, and this first eigenvector is near the limit eigenvector. And since this quantity is positive, we've been able to show that this quantity is also positive, and that's it. Of course, that's okay, a delicate analysis because this convergence here is in convergence of the compact set, as I said. So you have to control what happens outside the ball, a large ball. But okay, you can do it, and then we've been able to prove that this is positive, in fact. And then so I is positive, and that's the same thing. Okay. So that's it, and thank you very much.